Welcome to TechQuest X, where we make tech clear and show what it means for your roles. Most tech professionals assume Rust Wasm is primarily for running compiled code in browsers or serverless functions, right? But what if that narrow view is actually costing you monumental performance and portability benefits? This isn't just a developer concern. Here's what it means for product roadmaps, security postures, and even long-term architectural stability. The true power lies in its potential as a universal binary for complex backend systems, edge computing, or even advanced local LLM tooling. Unlike many topics where a simple analogy can instantly clarify, high-performance Rust Wasm demands a direct, architectural deep dive. There's no easy shorthand here, yet many teams focus purely on basic implementation. Basic Wasm implementation is a performance trap. They consistently overlook the advanced optimizations and architectural patterns that unlock its true, transformative power for demanding applications. This leaves significant performance gains locked away, becoming a quiet cost. Consider a mid-size SaaS company's ML team. They containerized a Rust Wasm inference model for a new personalization engine. 2 months later, customer support was swamped with complaints about irrelevant recommendations. The root cause? The Wasm module, while seemingly fast, wasn't optimized for cold start latency, forcing costly reinitializations for every user. 3 engineers spent 6 weeks diagnosing what was fundamentally an architectural oversight, costing thousands in lost productivity. This is an industry-wide blind spot. The how of high-performance Wasm often becomes secondary to the what of merely getting it to run. Serious professionals are quietly losing ground, paying a steep price in wasted compute, frustrated users, and delayed innovation for this fundamental miscalculation. But understanding this gap, this quiet tension between perceived utility and true power, is the crucial first step. Because what you don't optimize for will eventually optimize you out of contention. The performance and portability promise of Rust-based WebAssembly is incredibly compelling. Imagine near-native speed and consistency, running your critical logic uniformly across browsers, serverless functions, or even embedded devices. But that compelling vision often falls short of its true potential. Many developers stop at simply getting it to work, overlooking crucial architectural decisions and deep optimization strategies that unlock Rust Wasm's real power. You might be thinking, Rust is fast by default, isn't it? And yes, its core principles lead to highly efficient code. However, when compiling to Wasm, you introduce a new execution environment that demands specific, nuanced considerations. There's no single magic bullet or simple analogy for high-performance Rust Wasm. Achieving peak performance truly comes down to mastering several deeper, interconnected layers beyond the basics of writing functional Rust code. One of these critical layers is advanced compilation. This involves meticulous tuning of target features for specific platforms, applying link time optimization, and aggressively minimizing code size, aspects often neglected for faster build times. Then there's host environment interaction. Efficiently bridging between your Wasm module and JavaScript, Node.js, or other host runtimes requires careful management of foreign function interface, FFI, overhead, async boundaries, and data serialization. And finally, effective memory management patterns within the Wasm sandbox. While Rust's ownership model provides powerful safety guarantees, leveraging it optimally often demands strategies like zero-copy data transfer and memory pooling for maximal efficiency. Consider a small startup building a real-time data visualization dashboard. They deployed a Rust Wasm module for complex client-side data transformations. It lagged significantly with larger datasets, causing user frustration and churn. The root cause? They optimized the Rust code itself but ignored the overhead of frequent FFI calls between Wasm and JavaScript, and inefficient memory sharing patterns. 3 engineers spent months re-architecting critical components to address it. This isn't just a developer concern. It directly impacts user experience and therefore product adoption, a critical metric for product managers and growth teams. Simply compiling Rust to Wasm without this deep architectural thought is often just busy work, moving the bottleneck rather than eliminating it. Performance without deep architectural insights is, ultimately, just expensive guessing. Understanding these nuanced areas is the intellectual payoff, the moment you realize how to truly elevate your applications. But what happens when these optimizations are ignored? and you're stuck with truly poorly performing Wasm. While Rust Wasm promises incredible gains, a poorly optimized implementation is a hidden performance trap. Under-optimized Wasm is a silent budget killer. It can give the illusion of speed in simple benchmarks, but buckle under real-world loads. You might be thinking, but Rust is fast, and Wasm is efficient, and yes, in theory, they are. However, this isn't a simple concept with a catchy analogy. It requires a deep dive. The core issue often lies in the interface between your Rust Wasm module and its host environment, like JavaScript. An e-commerce team deployed a new Rust Wasm microservice for real-time transaction analysis. 2 weeks later, transactions started bottlenecking, leading to missed anomaly detections because the Wasm module frequently called back to JavaScript for simple I/O, incurring massive serialization overhead. This resulted in $10,000 in potential losses before the bottleneck was identified. Another common pitfall is inefficient memory management within the Wasm module itself. Without careful design, excessive allocations and deallocations can lead to unexpected stuttering. Then there are I/O bottlenecks. Blocking operations or transferring large amounts of data between the host and Wasm module can obliterate any performance benefits. Get this wrong, and you're not just wasting CPU cycles. This isn't just about developer cycles. It directly impacts project timelines, affecting PMs and budget holders who expect predictable performance. So what should you watch out for? Focus on minimizing host-guest calls, especially those involving data serialization. Leverage shared memory where possible, and profile your Wasm module meticulously. But what if the real optimizations are hiding in plain sight, waiting for a different approach? Many developers compile Rust to Wasm, assuming that raw speed is inherently guaranteed. But this often misses the deeper layer of performance. Raw speed without targeted optimization is just hope. True high performance in Rust Wasm comes from minimizing friction at the host-guest boundary. Optimizing these host bindings is crucial. And this isn't just a developer concern. Ops teams need to understand the implications for container resource allocation and scaling costs. Beyond Rust's robust memory safety, Wasm offers unique memory management opportunities. Choosing the right Wasm-specific allocator, such as wealloc or dlmalloc, directly impacts your module's binary size and execution speed. For example, a fintech startup built a critical fraud detection service using Rust Wasm. They initially saw inconsistent latency because their default Wasm allocator created unnecessary heap fragmentation. The fix was a targeted allocator switch, which saved them weeks of debugging and prevented potential reputational damage. Binary size is another often overlooked optimization frontier. Link time optimizations, or LTO, combined with tools like WasmOpt, aggressively prune unused code, yielding incredibly small, efficient Wasm modules. Then there's the emerging power of asynchronous Wasm. This is a game changer for I/O-bound tasks, moving beyond synchronous blocking and enabling highly concurrent, non-blocking operations directly within the Wasm runtime. Unlike a simple mechanical analogy, there's no single lever for Wasm performance. It's a symphony of subtle architectural choices that must be made in concert. These hidden optimizations fundamentally reframe the performance problem. It's not just about what Rust offers, but how intelligently it interacts with its Wasm host environment, maximizing efficiency. Ignoring these fine-grained details leaves significant performance on the table, and the implications for your deployment strategy could surprise you. The true power of Rust Wasm isn't merely about raw speed or clever coding. It's about engineering with a strategic vision, unlocking a foundational advantage for your entire tech stack. When Rust Wasm is architected for performance, it means lighter, more responsive applications. This directly translates to significant reductions in operational overhead and faster feature delivery. And conversely, ignore these critical optimization patterns, and you'll incur hidden costs. We're talking bloated binaries, slow load times, and constant resource drain that can sneak up on you. You might be thinking, my existing solution is fast enough. But fast enough today is often a bottleneck tomorrow. Chasing superficial benchmarks without architectural rigor is a fool's errand. This isn't just a developer concern. It profoundly impacts product managers planning roadmaps and operations teams managing cloud spend. Many teams rely on the illusion that Wasm alone guarantees speed. The reality is, without careful design, it can become another complex, underperforming component in your system, undermining your initial investment. Consider a mid-sized SaaS company with an internal analytics portal. They integrated early, unoptimized Rust Wasm components, promising near real-time dashboards to executives. 2 months post-launch, complex reports consistently timed out, leading to manual data exports. The root cause was neglecting Wasm-specific memory allocation and tree-shaking techniques. Every user load fetched excessive, unnecessary code, costing the data engineering team 3 months of refactoring and delaying critical business decisions. As we've seen, there isn't a single simple analogy for Wasm optimization. It's a mosaic of techniques. The path requires deliberate architecture, embracing tools like Wasm and Overlook not as add-ons, but as core tenets of your build process. This commitment to optimization differentiates. True performance isn't just fast execution. It's predictable reliability that scales effortlessly. It's the foundation of a lasting competitive edge. Thank you for diving deep into high-performance Rust Wasm with me. If this resonated, please like this video, share your biggest takeaway or challenge in the comments, and subscribe for more insights. The full playbook is linked in the description.